Hello students, I am Dilip Udani, Assistant Professor at LJ Institute of Engineering and Technology. Today in Sequence and Series, I will teach you new topic, that is absolute and conditional convergence and power series. So let's start. So first of all, we will see what is absolutely and conditionally convergent. The series sigma n is from 1 to infinite un is called absolutely convergent if the series sigma n is from 1 to infinite modulus of un is convergent. The series sigma n is from 1 to infinite un is called conditionally convergent if the series sigma n is from 1 to infinite un is convergent, but sigma n is from 1 to infinite mod un is divergent. So this is the theorem. If the series sigma un is absolutely convergent series, then sigma un is convergent. And you have to note down this important point. If convergent series is a positive term series, then it is absolutely convergent. So this was all about absolutely and conditionally convergent of given series. If sigma mod un is convergent for the given series sigma un, then sigma un is absolutely convergent. And for the given series sigma un, if sigma un is convergent and sigma mod un is divergent, then the given series sigma un is conditionally convergent. Now this is the example related to this topic. Determine absolute or conditional convergence of the series sigma n is from 1 to infinite minus 1 is to n into n square upon n cube plus 1. So here is the solution. Here un equals to minus 1 is to n into n square upon n cube plus 1. So first of all we will find out mod un. So we will neglect this term minus 1 is to n. So mod un, that is equals to n square upon n cube plus 1. So this n square will be as it is, and in the denominator taking n cube common, so into bracket we have 1 plus 1 upon n cube. 2 times n will cancel out, so this is equals to 1 upon n into bracket 1 plus 1 upon n cube. Now let Vn equals to 1 upon n. Here we are applying limit form of comparison test. Limit n tends to infinite mod un upon Vn, that is equals to limit n tends to infinite. Now see, what is mod un? That is this one, and Vn is 1 upon n. If you will divide mod un by Vn, the result is 1 upon 1 plus 1 upon n cube. Now as n tends to infinite, 1 upon n cube tends to 0, and 1 plus 0 is 1, and 1 upon 1 is 1, which is a finite and non-zero value. But sigma n is from 1 to infinite Vn, that is equals to sigma n is from 1 to infinite, Vn is 1 upon n, is a p series with p equals to 1. Therefore sigma n is from 1 to infinite, Vn is divergent. Therefore we can say that sigma n is from 1 to infinite, mod un is also divergent by limit comparison test. So here sigma mod un is divergent. So the given series is not absolutely convergent. Therefore we will check for conditional convergence. So here the given series is an alternating series, so we will apply Leibniz test. So for that purpose, first of all we will find out mod un minus mod un plus 1, and this is equals to, this is mod un n square upon n cube plus 1 minus, now in mod un replacing n by n plus 1, so it will become mod un plus 1, so that is n plus 1 the whole square divided by n plus 1 the whole cube plus 1. Now we will simplify this result. This term will be as it is, minus, over here applying the formula of a plus b the whole square, that is a square plus 2ab plus b square. So this is equals to n square plus 2n plus 1. Now over here applying the formula of a plus b the whole cube, that is a cube plus 3a square b plus 3ab square plus b cube. So it will become n cube plus 3n square plus 3n plus 1 and plus 1, it will become plus 2. Now we will simplify this result. LCM is these two terms, right? N cube plus 1 and n cube plus 3n square plus 3n plus 2. Now multiplying n square by this term, that is n cube plus 3n square plus 3n plus 2. This minus sign will be as it is. Now multiplying n square plus 2n plus 1 by n cube plus 1. Now we will simplify this result, multiplying this whole bracket by n square. Then after multiplying this whole bracket by n cube plus 1, and after simplification we will be having this result, that is n raised to 4 plus 2n cube plus n square minus 2n minus 1 upon these two same factors, that is n cube plus 1, n cube plus 3n square plus 3n plus 2. Now this n raised to 4 will be as it is. Now taking n square common from these two terms, so into bracket we have 2n plus 1. Then after taking minus 1 common from these two terms, so into bracket we have 2n plus 1, and in the denominator we have these two same factors. Now again we will simplify this result. We will take 2n plus 1 common from these two terms. Therefore, mod un minus mod un plus 1, that is equals to n raised to 4 will be as it is, plus taking 2n plus 1 common, and into bracket we will be having n square minus 1 upon, we will be having these two same factors in the denominator, and this is greater than 0. Now mod un minus mod un plus 1 is greater than 0, therefore mod un is greater than mod un plus 1. So the first condition is satisfied. Now we will see second condition, that is limit n tends to infinite mod un, and this is equals to limit n tends to infinite mod un is n square upon n cube plus 1. Now we will evaluate this limit. So this is equals to limit n tends to infinite. Now taking n cube common from the denominator, so into bracket we will be having 1 plus 1 upon n cube, and in the numerator we have n square, and over here we will be having n cube, so 2 times n will cancel out, and over here we will be having n only. Now as n tends to infinite, 1 upon n cube tends to 0, so 1 plus 0, that is 1, and again 1 upon n tends to 0 as n tends to infinite. So 0 into 1, the result is 0. So the second condition is also satisfied. Therefore, by Leibniz test, series sigma n equals to 1 to infinite, un is convergent. So the series sigma n is from 1 to infinite, un is convergent, but sigma n is from 1 to infinite, mod un is divergent. Hence, the series is conditionally convergent. Now we will see second example related to this topic. Determine whether the series sigma n is from 1 to infinite cos n upon n square, that is equals to cos 1 upon 1 square plus cos 2 upon 2 square plus cos 3 upon 3 square plus dash 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 is convergent or divergent. So here is the solution. Here un equals to cos n upon n square. Now mod un, that is equals to mod cos n upon n square, because n square is always positive. Now the maximum value of mod cos n is 1, so mod cos n upon n square, that will be less than or equals to 1 upon n square. Therefore mod un, that is less than or equals to vn. So here we are taking vn equals to 1 upon n square. Therefore sigma vn equals to sigma 1 upon n square, which is a p series with p equals to 2 and which is greater than 1. So sigma vn is convergent, and therefore series sigma mod un is also convergent by direct comparison test. Therefore the given series sigma un is absolutely convergent. Therefore, by the theorem, the given series sigma un is convergent. Now we will see power series. A series of the form sigma n is from 0 to infinite an x minus a the whole raised to n, that is equals to, for n equals to 0, an will become a0 and x minus a the whole raised to 0, it will become 1. So 1 into a0 result is a0. Then after plus sign, for n equals to 1, we have this term a1 x minus a the whole raised to 1. Then after plus sign, for n equals to 2, we have a2 x minus a the whole square plus dash dash dash. Is called a power series in powers of x minus a, or a power series about the point x equals to a. Here x is variable and an's are constant called coefficients of the series. Example, sigma n is from 0 to infinite x raised to n upon n factorial. This is equals to, for n equals to 0, you will get 1 because x raised to 0 is 1 and 0 factorial is 1. So the first term is 1. Then after, for n equals to 1, you will get second term, that is plus x raised to 1 upon 1 factorial. Plus similarly you will get these terms, that is x square by 2 factorial plus x cube by 3 factorial and so on. This is the power series in powers of x. Now we have one example related to this topic, that is, test the convergence of the series 1 upon 1 into 2 into 3 plus x upon 4 into 5 into 6 plus x square upon 7 into 8 into 9 plus dash dash dash, where x is greater than 0. So here is the solution. Here un equals to, consider 1 as x raised to 0. So we have x raised to 0, x raised to 1, x square and so on. So its nth term will be x raised to n minus 1. And for this sequence, that is 1, 4, 7, its nth term will be 3n minus 2. For this sequence 2, 5, 8 and so on, its nth term will be 3n minus 1. And for this sequence 3, 6, 9 and so on, its nth term will be 3n. Now we will find out un plus 1, so replacing n by n plus 1, so that is equals to x raised to n plus 1 minus 1, so it is x raised to n, divided by replacing n by n plus 1, so it will become 3n plus 3 minus 2, so it will become 3n plus 1. Now for this term, if we will replace n by n plus 1, it will become 3n plus 3 minus 1, so the result is 3n plus 2. And if you will replace n by n plus 1, it will become 3n plus 3. Now we are going to find out un plus 1 over un, and this is equals to, this is un plus 1. Now multiplying it by the inverse of un, that is this one. Now we will simplify this result. You can see x raised to n and x raised to n will cancel out. And in the denominator we will be having x raised to minus 1, so writing it in the numerator form, so it will become x raised to 1, and from here taking n common, so into bracket we have 3 minus 2 by n, similarly taking n common, so we have 3 minus 1 upon n, and this 3 will be as it is, and again in the denominator taking n common, so we have 3 plus 1 upon n. For this term taking n common, so we will be having 3 plus 2 by n, and again for this term taking n common, we will be having 3 plus 3 by n, and in the numerator we will be having n cube, and again in the denominator we will be having n cube, so n cube and n cube will cancel out. Now we will find out limit n tends to infinite un plus 1 upon un, so this is equals to limit n tends to infinite, this is un plus 1 upon un. Now as n tends to infinite, 1 upon n tends to 0, so this one will become 0, this 1 upon n will become 0, this 1 upon n will become 0, this 2 upon n will become 0, this 3 upon n will become 0, so this is 3 into 3 into 3, which is 27, then after this one is 3 into 3 into 3, which is again 27, so 27 by 27, that is 1, and 1 into x, that is x. Now by D'Alembert's ratio test, the given series is convergent if x less than 1, divergent if x is greater than 1, and the test fails if x equals to 1. Now put x equals to 1, then un it will be 1 upon 3n minus 2 into 3n minus 1 into 3n. Therefore un equals to, now taking n common from first term, then after second term, and this n will be as it is. So overall in the denominator it will become n cube, and into bracket 3 minus 2 by n multiplied by 3 minus 1 by n, and this 3 will be as it is, and this 1 which is in the numerator will be as it is. So this is un. Now here we are going to apply comparison test. So let Vn equals to 1 upon n cube. Now limit n tends to infinite un upon Vn, that is equals to limit n tends to infinite. Dividing un by Vn, we have this result, that is 1 upon 3 minus 2 by n into 3 minus 1 by n into 3. Now as n tends to infinite, 2 by n and 1 upon n tends to 0. So we have 1 upon 3 minus 0 into 3 minus 0 into 3. So which is 1 upon 27, and which is a finite and non-zero value. Now sigma Vn, that is equals to sigma 1 upon n cube, is a P series with P equals to 3. Therefore the series sigma 1 upon n cube is convergent. Therefore by limit comparison test, sigma un is also convergent for x equals to 1. Hence the given series is convergent for 0 less than x less than or equals to 1, and divergent for x greater than 1. Now we will see second example. Test the convergence of the series sigma n is from 0 to infinite, n plus 1 upon n plus 2 the whole raised to n into x raised to n, where x is greater than 0. So here is the solution. Here un equals to n plus 1 upon n plus 2 the whole raised to n into x raised to n. Therefore un the whole raised to 1 upon n, it will become n plus 1 upon n plus 2 into x. So here we will apply root test. Therefore limit n tends to infinite, un the whole raised to 1 upon n, this is equals to limit n tends to infinite, this is un the whole raised to 1 upon n. Now taking n common from the numerator and denominator, so we have n into bracket 1 plus 1 upon n into bracket 1 plus 2 upon n, and this x will be as it is. Now n will cancel out. Now as n tends to infinite, 1 upon n tends to 0, and 2 upon n also tends to 0. So it will become 1 plus 0 upon 1 plus 0, so that is 1 upon 1, so that is 1, and 1 into x, the result is x. Now by root test, the series is convergent for x less than 1, divergent for x greater than 1, and the test fails if x equals to 1. Now put x equals to 1, un equals to n plus 1 upon n plus 2 the whole raised to n. Now limit n tends to infinite un, that is equals to limit n tends to infinite, taking n common from the numerator and denominator, so it will become n raised to n into bracket 1 plus 1 upon n the whole raised to n divided by n raised to n, so into bracket 1 plus 2 upon n the whole raised to n. Now n raised to n and n raised to n will cancel out, and limit n tends to infinite, 1 plus 1 upon n the whole raised to n, its value is e, and limit n tends to infinite, 1 plus 2 upon n the whole raised to n, its value is e square. So e upon e square, that is equals to 1 upon e, and 1 upon e is not equals to 0. Hence the series is divergent for x equals to 1 by nth term divergence test. Hence the series is convergent for 0 less than x less than 1, and divergent for x greater than or equals to 1. So in today's lecture we have discussed absolute and conditional convergence of the series, then after convergence and divergence of power series, and examples related to this topic. Thank you for watching this video. I will see you in the next lecture.